Hello, this is the final presentation for Group 3, predicting CTA usage using ridership, demographic, and socioeconomic data. The CTA, or the Chicago Transit Authority, operates one of the nation's largest public transportation systems. Due to the city's demographic and socioeconomic changes over time, the efficiency and accessibility of public transportation may not be as reliable or as optimal as it once was and has the potential to be. With this project, our goals were to utilize the publicly available CTA ridership data with detailed demographic and socioeconomic info from the US Census Bureau to develop a robust model capable of accurately predicting CTA station usage. We also wanted to create a predictive tool that could be applied to the newly planned Red Line stations.
All right, we're going to do a quick overview of the exploratory analysis for the CTA and the Census Bureau data that we took. So just to go over where we got the data from to start, we pulled 4 data sets from the CTA's publicly available data. That's going to be L station entries, which has the entries every day for every L station in the system, annual ridership data, daily ridership totals, and the L station locations, which is how we're going to get the geographic data for them. From the Census Bureau, we downloaded housing data, income and education, gender and age, occupation and commute data, and then we filtered out all the Illinois stuff, so it's just the 6 counties from around Chicago.
So we also got the crime data from the Chicago data portal, and apart from that, we also got the this housing data, basically the sales data from Cook County's Assessor's Office, and also the hardship index data, which was also gathered from the Census Bureau.
These are the kind of variables you can see here. There's a lot of them, but you'll see they all relate back to one of those 4 categories. So we have occupation status in the or type in the front, and then we have commute, housing they have, income, education, etc. And then these last ones here are historical ridership data. So A 2020, you see here, it's Saturday ridership for the given year. So that's Saturday ridership for 2020. So, and those are averages. So here's the target variables. As I said, U, Sunday holidays, A, Saturdays, W is weekends. That's how the CTA codes the day types. There's 3 of them they use like that. And then the target that we're going to be trying to predict will be the 2023 usage for each type of those days. So it's going to be A-2023 like that. Some of the quick visualizations we did for exploratory analysis. We can see here, this is the trend of total rides over time. And basically, we can see a couple of things here. One, that giant spike is the Cubs World Series win. So that's why it's so much higher. A lot of people came down. And then you can see here, COVID made a huge impact, and it's not quite returned to normal yet. So you can see the distribution of usage, and obviously weekdays is predominant, and then less on Sundays and Saturdays. Here we can see the top 10 stations for weekdays versus weekend, and you'll notice a few differences. You get a lot more commuter stations downtown, like Clark and Lake, Lake State, Chicago State, and 95th Dan Ryan. That's the end of the red line. So I think a lot of those are people using it for work. And then on the weekends, you'll see some differences here. You still have Chicago and State downtown, but then Belmont is the Cubs Stadium stop, and then O'Hare Airport for trips. So there's a few differences there. And then here we have the top 10 days with the most ridership, and you'll notice that they're all actually related to the Cubs. So Belmont and Addison are both stations to get off to get to Wrigley Field, and then the Clark and Lake and State and Lake there are actually the same date as the Cubs downtown victory parade in 2016 for the World Series win. So oddly enough, all of the most used days or the biggest rides are all Cubs related. So we're going to get moving to some distributions for the census data. You can see here median age is pretty evenly distributed with a bit of a skew, with a few outliers there. Same with median income. We do have one outlier way down at the 200,000 mark. Here we have the distribution of age groups. Again, pretty standard, drops off a bit as people get older, as you would expect. And then education is also pretty much normally distributed. Departure times and commute times are a little bit different. Obviously, most people, as you can see, are going to leave between 9 and noon to go to work, and a few smaller groups leaving earlier than that. And then the commute times, you can see it's pretty even actually, with the exception being the strange drop for 25 to 29 minutes. Distribution of occupations is a little bit, obviously that won't be normally distributed. And these are all categories made by the CTA, which is why it says like management, arts, and science professionals. They combine that into one category for whatever reason, so we had to go with the categories that they chose. And then you can see the distribution of race, predominantly white, black, and Hispanic, with smaller groups of Asian. All right, we're going to go over some of the model development now using the CTA and census data. So our goal was to be able to predict the CTA station usage based on the data we had. And I'm going to go through the first couple of models that we tested. So we're going to do just some basic regression, some ElasticNet, and some SVM models as well. So first, we had to prepare the data. This included a lot of merging the different data sets together, and then using this Tigris library to assign census codes to make sure we could match everything up with the correct census data. Tigris is a library that is specifically meant for handling census data in R, and there's a Python version as well if you're interested. And then we aggregated the station entries into daily averages, basically, for each day type for 2020 to 2023. We took 2020 forward because of the COVID pandemic related drop. We didn't want to use historical data from before that because it was a very different pattern. And then we added 4 new redline stations that are part of the extension project that they're doing. And we had to fill in some missing data for Berwyn and Lawrence stations with averages of the closest stations to them. And we did the same thing for the stations that are added on the extension. Since they aren't completed yet, there's no historical ridership data. So we picked the 4 stations that are the end of the line on the red line and average them to create historical data for these 4 that will be the new end stations. So the first model we tested was just a basic linear regression model without the historical data. We wanted to do this just to see how well the census data alone could predict the station usage. You can see that the first chunk here is the results from that with a multiple R squared of 0.76 and adjusted R squared of 0.37. So not particularly good. That's sort of what we learned here for the other 2 models here as well. The second one we used PCA and tried it again. And the third one we did PCA, but we used stepwise selection to specifically select PCs, so we didn't use all of them. When we did PCA on the data set, it created about 100 PCs, or I think 92, which was still too many. So we tried to apply stepwise selection to only pull out the most significant ones. And that did work better. You can see the adjusted and multiple R squareds are a little bit better there, but still not great. So we basically learned that we were going to need to add the historical data in to make sure that we could create accurate predictions. So as I said before, we added back the historical data. We did PCA again. Unfortunately, this led to a large amount of overfitting the model. You could see multiple R squared and adjusted R squared of 0.99. The second attempt here we did was extracting only the most significant PCs, and that did a little bit better, but it was still overfit. You can see we went to 0.92 and 8.7. So we still thought we could improve on this more. We also attempted to use SVMs to see if they performed any better. We used 3 different types of SVMs and applied grid search to find best parameters. These did not perform any better than the previous models, so we decided to move on. So we decided to try ElasticNet, and this is where we had a lot more success. ElasticNet, if you recall, is the combination of ridge and lasso regression. We use PCA, tenfold cross-validation, and a grid search for the alpha and lambda values. The alpha value, if you recall, is it's between 0 and 1, and it changes between ridge and lasso depending on how far along that scale you are. And lambda is the penalty value. So we created 3 models, 1 for each target variable. So Saturdays, weekdays, Sundays, and holidays. And these all perform much better. You can see our test RSMEs here. And there's a table at the end here I'll show you that compares all the RSMEs because that was the test metric we used. So when we plotted the predictor actual values, on the left here is for the ElasticNet model, and compared that to one of the original stepwise linear historical models, you can see that it's a lot tighter and our predicted values were a lot closer to the actual values. So these ones are working much better. And here's our final model comparison. We've got linear scale data at the top. Those are the first models I talked about. As you move down, you'll see the RSMEs. And at the bottom are the 3 ElasticNet models that we had the most success with. And all of those were about 300, 313 and under. So they perform better than any other. So our conclusions for this, though, were that ElasticNet models were the most effective for predicting CTA ridership, and they outperformed the other models significantly, with only the linear SVM, having a RMSE of under 602. So we thought that these models could be applied to predict new stations' daily averages, and they could be applied to other CTA projects, not just the Redline extension. But using these models, we did predict what we thought that the new ridership would be daily for weekdays, Saturdays, and Sundays. And that's what this chart says here. So you can see what our predictions would be.
So once we got a clear idea of the ridership patterns in the CTAL and where to implement a new station, we'll be looking at how this new CTAL line will be affecting the neighborhood housing prices and also the crime rates around this CTA. So to begin this analysis, we firstly merged multiple data sets, including census data, crime, CTA, and sales data, using a unique identifier for each neighborhood, basically, which is the column GeoID. So this consolidation allowed us to leverage comprehensive insights from various sources. Next, we address missing values in the data set. So we either null imputed them or dropped those rows. Apart from this, we also did transformations, and we standardized the formats for sale prices and ages to ensure consistency and compatibility. So once the pre-processing steps was done, we ended up with a data set which had about 400K rows and 32 columns. So to streamline our analysis, we further divided this data set into training and prediction subsets. So the final data set after merging had the following features from each data set. For example, from the demographic data set, it has total population median age, whereas from crime, it had total number of crime. From transportation, it has distance to the nearest L in miles. And from sales and attribute, it had number of sales, average age. And from neighborhood, it had dummy variables for each neighborhood, like the Hyde Park, Lincoln Park, and all. So we did some exploration as well of the data set, and we can see on the left side, we can see the total number of crimes happening in the Chicago for each of its 77 neighborhood. Followed by that, on the right, we can see the median sale prices for each neighborhood, where we can see North and Center on the top, followed by Sheffield and DePaul, Bucktown, Wrigleyville, and Lincoln Park. And similar on the bottom, we can see the South Chicago, there's Riverdale and all. So basically, the blue color indicates the north side and the red indicates the south. We can see most of the blue color that is in north are having the higher prices, whereas the red is having the lower prices. So from this, we can see there's an inverse relationship between housing prices and crime rates for each of the Chicago neighborhood. We can see the north has higher housing prices with lower crime rate, whereas generally the south side, like Fuller Park, has lower housing prices with the higher crime rates, whereas Loop is an exception as it's like a business hub center where people do travel for their work. So with the training data set that I had, I created a non-temporal 5-fold cross-validation to ensure robustness and to prevent overfitting. And apart from this, each train set is split into 5 folds randomly. So this is used to clearly understand how the past data is used for temporal training and validation. Apart from this, I ran numerous regression models, which include linear, ridge, lasso, ElasticNet. Followed by this, I also ran decision tree, random forest, and gradient boosting. So coming to the evaluation metrics and model selection, we can see that the linear regression model is performing inadequately, suggesting the need for more sophisticated parameters. We can see the rest of the models are performing similarly, and when we see the right side plot, we can see that specifically random forest is performing very well with its RMSE value compared to the other model. So here's a chart for each model for linear regression, ridge, lasso, ElasticNet, we have our decision tree, random forest, and XGBoost. We can see the RMSE value for each, and we can see that for random forest, it has its RMSE very less compared to the rest of it, with its parameters being max depth 40, max features square root, minimum sample split 2, and estimators to be 100. So once we get the parameters for our random forest, we predicted the housing prices for the upcoming years for the GeoID. So we can see that is presented in the table in the right for the year 2023 and 2024. Also, from the image on the left, we can see I've also shown the top 15 important features from our random forest model. We can see the inclusion of normal distance mile, which is an influential factor, suggests that proximity to CTA lines indeed impact property pricing, and also the crime rates. So our analysis revealed that areas closer to new CTA lines experienced observable changes in both housing prices and localized crime rate. So this finding aligns with our initial hypothesis, indicating that transportation infrastructure developments can have significant socioeconomic implications on urban neighborhoods.
Hello, so I will be discussing how the data was visualized geospatially with QGIS. So the first step in this process was developing a foundational map layer, and this was done by mapping out the rail lines and their stations for the CTA rail line, or CTAL. And the purpose of this was to develop a foundational map to serve as, like I said, the anchor when visualizing or overlaying the other geospatial ridership data and census data. And ultimately, this is to aid in identifying patterns or trends or other insights that may not be as easily visible through traditional graphs or models. So here we have ridership data visualized geospatially, and this is done by average ridership in terms of density per stop. So that's why you see some circles are larger than others. The larger circles are for more dense ridership stations compared to the smaller circles. The next data type that was visualized was crime. As you can see, different types of crime were visualized using the foundational map as the anchor. And already in a zoomed out view, you can see that there are certain concentrations. While very dense, you can still see that there are clusters, or like I said, certain concentrations of different types of data. For example, narcotics is fixated a little bit more out of the city to the west compared to north and even south. So just looking at those to see if there's something that could be uncovered, that was a part of the visualization procedure and kind of analysis experience. Continuing on with the geospatial visualizations, we have population, and this example is population by race. In this specific case, we have white, black, Asian, and Hispanic that were visualized here. And as you can see, there are definitely certain concentrations or areas that are more dense than others for the different races or ethnicity that are featured here. Continuing on with that, we have population by income. Like I also said again, you can see the different concentrations or, dense areas based on different income brackets as you get up to 100,000 plus. So the two rightmost visualizations, you can see that, the higher the income, the, less present those individuals seem to be. Likely that is because they don't live in the city and perhaps live in the suburbs. So items like that are and insights like that are things that are being noticed and looked for in this kind of exploration visualization procedure. So transitioning from exploration or explorative visualizations to more analytical perspectives. An example of this that was performed was looking at population and looking at income and race in terms of population. Up at the top here, we have white, black, and Hispanic, and then taking those identified dense areas and evaluating those areas in the different income brackets and seeing what could be uncovered or discovered with those comparisons. This case in particular, when it comes to visualizing race and ethnicity paired with income, that helps us identify the different disparities and accessibility issues in terms of regarding the transit system. It also helps us identify the demographic factors that influence ridership patterns or usage. So, elements like this are really, really insightful when it comes to being able to geospatially visualize the data, apart from just visualizing graphs and understanding the different figures that come up in the different models.
We also looked into hardship index data to see if that would provide any additional insights. The hardship index data comes from the UIC Great Cities Institute and the US Census Bureau. It includes information on the conditions of economic and social hardship within Chicago community areas from 2016 to 2020. The score is the average of 6 standardized variables: percent of crowded housing, percent of households with income below poverty level, unemployment rate for population age 16 and over, percent age 25 and over with no high school diploma, percent of population under age 18 and over age 64, and per capita income. This index is used to examine the conditions of economic hardship or the difficulty resulting from not having enough collective economic resources available. There are 77 community areas within Chicago. The hardship index score for those community areas ranged from 9.4 to 76.5 with a mean of 44.66. The community areas with the highest hardship index scores were Riverdale at 76.5, Fuller Park, West Garfield Park, Englewood, and New City. The areas with the lowest hardship index scores were near North Side, 9.4, near South Side, Lincoln Park, The Loop, and Lakeview. We combined the hardship index data and the CTA data based on the community area. We used this to find the number of stations within each community area. We also updated the data set to include stations that were considered part of 2 different community areas twice. So there were some stations that were located on the edges of 2 different community areas, and we decided to include those stations twice, as this more accurately reflects the community areas that have stations versus just having the correct number of stations. We then created a simplified data set with the number of stations and certain columns from the CTA set related to income, population, education, and race, plus the station data and the associated hardship index score data. The goal here was to expand on the hardship index data and get a better understanding of how those variables, income, population, education, and race, relate to the community areas and the availability of public transportation. We created 2 models with the goal of predicting the number of stations within a community area. For linear regression, the test R-squared was 0.688, and for ridge regression, using 5-fold cross-validation, the test R-squared was 0.708. So neither of these models was super successful at predicting the number of stations, which makes sense given that I think there are a lot of other different factors just besides socioeconomic factors that go into how many stations have been created within an area.
There's also some future work we think that we could do here to continue the project.
So that was our presentation. Once again, we are group 3.